Hello everyone. I thought it'd be kind of fun to show this presentation I did called From Language to Logic, Understanding and Applying AI Models in Speech-Language Pathology that I gave for SLP Tech Talk. And it's focused on how SLP, the field, and practitioners can use and understand large language models at sort of an overarching high level. Now, I do actually plan on eventually delving more deeply into specific topics from this, but I just wanted to kind of give this overview lecture that I gave that I was kind of explaining what large language models are and how they can be used for SLPs. So the topics that I'm going to look at are, first, I'm going to look at large language models. I'm going to look at reasoning models, and then I'll look at deep research models. Then I'll look at a comparative analysis very quickly about the different types of models and what they're useful for, what their pros and cons are. Then we'll look at some applications that can be useful for SLPs, speech-language pathologists. And then, of course, I'll briefly talk about some of the ethical and practical considerations that there may be based around this topic. So first of all, let's look at AI models in clinical practice. So why would you want to use AI models for an SLP? So AI tools are rapidly evolving and becoming accessible in healthcare. Many of these systems are built on these language models, and these help us to understand, I say in quotes, and generate human language. Now, the reason I put understand in quotes is because there's a term called stochastic parrots, which describes what these large language models actually are, and I'll briefly talk about that as well. And we also want to look at understanding how they work to empower clinicians to use them safely, effectively, and ethically. Now, what this talk is going to cover is we're going to look at three key AI model types, which are going to be large language models, reasoning models, and deep research models. Now, and we're also going to look at how these models apply to clinical tasks, assessment, and research in SLP. And then we want to look at what these models can and cannot do, or in some cases, should not do. So first, let's talk briefly about the three different types of models. So we have large language models, often called LLMs, which are trained to understand and generate human language. You have reasoning models, which are built to solve problems using logic and multi-step thinking. And then you have deep research models, which are designed to gather, evaluate, and synthesize complex information. So let's look at large language models first. So large language model, again, is designed for language-based tasks, foundational for more of our complex models. So the definition is that it's a neural network that's trained via self-supervised learning on massive corpora of text. That is to say, in layman's terms, that these companies or organizations have gone out and collected anything and everything they can in written and now, of course, with visual and auditory text that is created by people. So this could be books, this could be how-tos, this could be blogs and vlogs, this could be websites, anything and everything that is based on human speech that they could get their hands on, they would put together in this neural network to train these large language models. Now, self-supervision means that the model will generate its own training signals. That is to say, it's predicting masked words or next tokens. So what this means is while there might be some framework on how it's trained, it's going to determine how it evaluates what should come next. And this is, again, where the stochastic parroting comes in. Because what a large language model does is it's really sort of an autocomplete. It's a very advanced, complex autocomplete where it is trying to figure out, based on tokens, which I'll talk about in a second, to determine what is the most likely correct response based on what was given to it. And then from there, it's going to add a certain level of randomness, that's the stochastic part, to not always give you the exact same answer every single time. So this architecture is based on what's called a transformer networks, which was introduced first in this paper by Google Brain called Attention is All You Need. And it uses multi-head self-attention to weight relationships between tokens. So tokenization is just, its text is converted into numbers via schemes by things like byte pair or word piece, where every single word or word sequence or word spacing or punctuation, anything like that is put into a numbered token. And then we look at how these tokens are related to each other to create weights. Now, this is where that attention comes in, because this was the big breakthrough they made there. Tokenization had been around for a long time. But what they did is they focused on attention, which has to do with relevant tokens based on a topic. So for example, if I'm referring to something in biology and it starts seeing a lot of words that are linked together by biology, then words that are related to biology will have a higher weight or attention associated with them. Whereas if I'm talking about something completely off topic, like the newest trends online, then this wouldn't have as much weight for this particular question because it's using attention to weight which tokens are most relevant to what's being asked. Now, one of the trade-offs in the architecture is that there is the context window size, which has to be considered. So this is a trade-off between what's called a local or a long-range context. So most systems will have some range of token values that they will use in their modeling. So if I have an overly long text, it may have a context window that's too short for that, and I need to focus on localized text, let's say a paragraph or a page or 100 pages, where I may have a 300-page document where it's going to be outside the context window of tokenizing in order to generate my answer. Now, for this tokenization, our vocabulary is optimized for English, which increases token load for other languages. So this is something that has to be considered. Most are focused on specific languages. Therefore, if they're trying to bring in outside languages, which maybe have less context for, stuff like that, it will lead to an increased load when they're actually processing all of this. Some of the capabilities that these models have is focusing on syntax, semantics, ontology pattern learning, and it will focus specifically on language generation, summarization, and translation. The limitations of a large language model is that it inherits biases and inaccuracies from its training data. Remember how I told you it brings in all that corpora, all that text to train the models? Well, this is going to inherently bring in any biases based on that data. And also, these models can specifically not reason, calculate, or access real-time information without some sort of augmentation. There are enhancements to this, for example, using Retrieval Augmented Generation, or RAG, which is an external vector-based document retrieval, which will help to improve factual grounding. That is to say that it can actually make references outside the system to then try to strengthen the answers and results that it gives. For clinical implications for SLPs, this will allow things like automated note-taking and therapy documentation, generating age-appropriate language exercises, and text simplification and translation support. Next, we have reasoning models. So reasoning models are an AI model that's trained to perform multi-step reasoning and problem solving. The way that it works is you actually start with an LLM, a large language model, and then it's going to be fine-tuned on reasoning data sets with traces for reasoning. And then this is further trained using reinforcement learning, things like proximal policy optimization, which will then allow it to kind of create these reasoning chains, which then will allow it to link more complex task than just here's text, what is the most likely response based on the tokenization of this text. So the mechanism is that it uses reasoning tokens and internal chain of thought generation to then try to figure out what is the most likely answer. So it's still based on those large language models, but now it's using these reasoning tokens to try to give you a more accurate answer. So what it does, it will build a search tree of parcel solutions, and it also has the ability to go back and backtrack once it finds certain branches that either have a good probabilistic strength or ones that are weak. As it prunes them off, it can go back and then also restart the process, and this is part of that chain of thought. Now, some of the characteristics of a reasoning model is that it is more computationally intensive than a large language model. And it has slower generation due to what's called stepwise reasoning, where that is to say that as it goes through that reasoning chain, and if it, of course, has to backtrack, this means that it adds more steps, which means that it will have slower generation. Now, the applications where reasoning models really stand out are for coding, scientific problem solving, and planning what are called agentic workflows, where agents have to do with systems that have specific tasks that they do outside the actual model, but are connected to it. Some clinical implications for SLPs are AI-driven differential diagnosis suggestions. It also could help with logical flowcharts for therapy and decision-making, and also can allow for dynamic patient modeling for treatment personalization. This brings us to deep research models. So these are autonomous agents that plan, search, read, and synthesize information on the web. So specifically, this is an agentic system that's based on a reasoning model that performs a multi-step autonomous research. So what this means is you have a large language model, and then reasoning models are built on top of that. Well, then a deep research model is then taking that reasoning model and then it is adding in this search research functionality to give even better responses based on the query that's being given to it. So its components and workflows. First of all, planning. It breaks tasks into subproblems. The first thing that these deep research models do is they break the task into a bunch of subproblems. And then it'll use tools like search, browsing, and retrieval to then go out and find specific documentation or whatever it needs for those particular problems. Then synthesis. It will gather and organize this information into structured, cited reports. And then one of the things about these deep research models is that oftentimes they can actually be made up of many submodels representing the different tasks that it broke each part into. And then you have this overarching model, which is kind of taking the bits from each one and creating a more comprehensive answer. And then from there, if one model has something, it might actually be able to change something that is in another model for another subtask. So you sort of have this overarching orchestrating model that's controlling a bunch of sub-reasoning models. It uses asynchronous task managers to maintain the state, and it can recover from failures and continue tasks, because unlike a reasoning model where if it fails, it's failed, now because you have this overarching model, if one of the models fails, it can actually restart that process from where it was or starting over because it's keeping track of the task itself. These deep reasoning models generally have large context windows for multi-turn reasoning, because the idea is that you want to take it even further by adding this deep research component to it. These are effective for knowledge-intensive tasks. For example, this can produce verifiable cited outputs because unlike our large language models, which weren't really connected to the web, it can actually go out and find sources to cite what it's making its decisions based on. This will allow it to, again, produce verifiable and cited outputs. And it can also find non-obvious insights across multiple sources because it's pulling all these sources together, having the individual agents do what it asks it to, and then it may actually update, it self-updates based on what the different ones find. Now, there's some clinical implications for SLPs are they could allow for automated literature reviews for case-based interventions. It could allow rapid synthesis for best practices from current research, and it can allow for generation of evidence-based materials tailored to specific populations. So now let's do a quick comparison of these different models. So the strengths of each model are that large language models are great for when you want to deal with just language-specific tasks. That is creating text, altering text, trying to decipher what is in text, things like that. Reasoning models are great for logical planning and multi-step inference, whereas in deep research are great for when you want to add search and synthesis and then also get verifiable reports from whatever you're querying. What they're best for is that large language models are best for routine text task documentation and text simplification, whereas in reasoning models are great for things like decision trees and dynamic planning tasks. And then deep research is best for evidence-based practice and research translation. Now, they do each have their own limitations though. LLMs are often limited in their logic. They do not have access generally to outside information other than what they were trained on. And they have a lot of factuality issues, meaning specifically hallucinations, which means that it will give you an answer, whether it's right or not, and it will make it come off very much like it's a correct answer, right? It will confidently be wrong. And this is one of the big things a lot of people have noticed with large language models, is that they are meant to give you an answer. And if it can't find the answer, it is going to basically give you what sounds the best. Next, we have reasoning models, when their limitations are they have high compute times and they're still language bound, right? Because they're built on those large language models. So they do still have all of the limitations of a large language model underlying them to some degree. Now, some of the aspects of them help to eliminate some of it. For example, its multi-step processing may be able to help eliminate some of the hallucinations. Deep research is the most complex, which of course then means it's the most resource intensive. So for computational and capability scale, large language models are smaller in scale, though still very large scale, hence the large. They're much smaller in scale, though, than reasoning models, which are less resource intensive than deep research models. So some administrative tasks that these models could help with are things like SOAP note generation. Now, this is a standardized method of documenting patient encounters in healthcare. The SOAP stands for Subjective, Objective, Assessment, and Plan. This could be things like dealing with speech recognition and AI summarization, allowing practitioners to generate this documentation in a much faster manner. It also can be useful for intake form analysis. It can help extract key information and flag issues that may come up based on if you have especially some very uniform documentation that you're using or a uniform process like SOAP. Also, it can help categorize client data for scheduling and caseload assignments, and it can also help generate summaries for EHR and initial report. We could also look at, again, with uniform documentation, you can have insurance form preparation where it can help autofill repetitive information or summarize clinical justifications. So these are some of the administrative tasks that AI systems could be useful for. For therapy and assessment, you could have personalized exercise generation. So this would allow SLPs to tailor to client goals and incorporate interest based on the patient. You could also look at helping with multilingual support, whereas an SLP may only have limited ability to help in a language where a LLM might be able to help expand on that a little bit and adapt their systems for it. It also could help with things like question simplification or augmentation, right? It could generate scaffolds or prompts or follow-up questions based on what's occurred in the conversation before that. It could also allow to expand questions to focus on specific skills, and it can also adapt questions from existing materials, right? So if I give it a bunch of materials, and it's actually a lot of my research focused on this, is if we have these materials, can we use these LLMs to then take new materials and figure out things from it for people who are not practitioners, or can we specifically adapt some material to use for some sort of learning training, something like that. And then also, one of the big ones, it can help with things like adaptive difficulty tuning. That is to say, if you have a patient who is doing very well, you could increase the difficulty by having the system automatically kind of up the difficulty. Or if the patients are particularly struggling, it might bring down the difficulty some to hit sort of that sweet spot where the difficulty should be for the patient. Which is why I wanted to really focus on this adaptive difficulty tuning, which modifies task complexity based on client's response. And it can also help maintain optimal engagement and challenge with the client who you're focusing on for whatever zone of proximal development that you're dealing with. It also can focus on specific skill progression, right? So it can adjust task difficulty along a developmental continuum. That is to say, it can increase linguistic complexity, or it could be reducing visual support, things like that, as you kind of increase the difficulty to reach a specific goal. It also allows us to track progress over time. So we can learn from our clients' data to then personalize future assessments and gradually increase the demands based on the prior and current lessons. And also it can allow real-time feedback loops, which can be used in digital tools to kind of automate some of this process. Now, what about professional development? For professional development, these can be very useful for doing things like summaries of recent journal articles. It's really hard to keep up with all the most common and modern research that's going on, so oftentimes it can be useful to condense research into key takeaways that a practitioner might be interested in. Rather than reading through all of the actual academic literature, it could actually help, if nothing else, create a framework for you to focus on specific things that might be relevant to your specific practice. You can also use it to customize topics by interest, right? Wherever your interest is, if you're focused on bilingual learners or people who have speech impediments, things like that, it can actually help you find and focus on those particular areas of interest. It can also be used for personal development to help assist development of training modules. Things like you can align content to best practices, adapt to different audiences, and even adapt to multiple delivery modes, right? So it could be things like if you're having classroom environment versus online versus some sort of automated system where people train and keep up with the most recent practices in the field. It also could be especially useful if you're in the research side of things for planning for clinical studies. But now it's time to talk about probably one of the most important topics around the whole thing, which is the ethical considerations. So a few things you have to consider when you're looking at using these systems are things like data privacy and HIPAA implications, right? So you need to focus on maintaining client confidentiality, compliance with HIPAA or FERPA, You also need to look at the risks of cloud-based tools, right? You're always hearing about different leaks or systems getting broken into. You also really need to focus a lot on de-identification. But the problem is that de-identification is not always sufficient, right? Given enough data about different clients, even if they're de-identified, you can oftentimes trace back to the identity of the particular person. Second thing you have to worry about is the risk of hallucinations and how you can mitigate that. And this is where human oversight is essential, right? And I specifically want to focus on domain expertise because this is one of the biggest issues with large language models and their ilk right now, is that too many people are using it as a replacement where you really need some level of domain expertise to assess and also confirm what results you're getting from those large language models. This is a problem I see a lot of times with students, is that students will just take a response and they'll just post it as if it's their own. It's doing the thinking for them. But they don't have the necessary background to assess. Yeah, remember, the whole point is that these models are made to sound correct, even if they are incorrect. We call it confidently incorrect. It will give you an answer like, oh yeah, super easy, here's how you do this process. And it won't be right. But the student won't know because they're offloading the thinking to the system. And this is why domain expertise is so important, because just because you get a response and it sounds correct, it sounds right, you still should, one, make sure you have some understanding of the topic and also go and verify what it's giving you. You should focus when you're creating, working with these systems, is to use structured prompts and reliable sources. Now, some systems are better for this than others. Some systems will actually show you the cited sources, which I would highly recommend. If you're using one of those, go to the cited sources. Do not just trust those exist, because part of the hallucinations can be the sources. In fact, if you go online and look it up, you will find a lot of articles about lawyers, even researchers, who have put out something saying they're citing this and it doesn't exist. Next, you'll have the need for clinician in the loop approaches. That is to say, we want to ensure the human oversight in decision making, right? So the idea with these systems is that they can assist in a lot of these tasks we've talked about, but in the end, a human should still be in the loop, looking at, one, using domain expertise to verify things, but also to make final decisions. This will allow for supporting iterative refinement, which means that then the person who is making decisions can then refine these processes to hopefully make them better over time. It also will help maintain contextual awareness, and it helps to mitigate the risk of automation biases, right? We talked about every one of these models has bias inherent in them. So a lot of times with a human in the loop, you might be able to flag and or eliminate some of those biases. The last thing we need to focus on, though, specifically are those biases, fairness and interpretability. So again, there is bias in the training data. In machine learning, we often say garbage in, garbage out. It doesn't matter how smart, complex, advanced your model is. If you have biased data, you will get biased results. Also, you have to consider things like equity in language and content. This would be things like, for example, some of the research that I've worked on, we worked with child's word learning development and comprehension. Well, the problem is most text online, on the internet, in books, is written for adults. So this means that while I may get answers that seem correct from an adult perspective, they may not be appropriate based on the people that we're focusing on, which in this case would be young children. So in this case, it's not really, the language is not really equitable for a child versus an adult, and the content may not be right where it needs to be. You also have to consider interpretability effects and trust in use. What you want to do is you want to evaluate AI outputs across different groups, right? Demographics, things like that, to make sure that your system is actually doing what it's supposed to do. And then that last thing is you really should focus on promoting transparent and explainable systems, right? A big problem we always have in machine learning is what are called black box methods. And oftentimes these could be things like reinforcement learning, which are exceptional at getting really good results, but they don't allow explainable results, meaning that while we might be able to make an assessment and be correct most of the time, we don't have the ability then to say why it's necessarily correct. So in this case, when you're dealing with people especially, you should always kind of focus on this, right? Not always just what does the model say, but also why is this true? And this allows us to have approaches which are more focused on the particular problem and clients or patients. But in conclusion, the idea of this is that large language models are a tool. And like any tool, they can be very useful. But what's important to know is which model will suit different SLP purposes, right? So if you just need help with generating some text for some exercises, a large language model would be great. If you're trying to create some logical flow for flow charts, deciding how you're going to approach some case, you might want a reasoning model. If you're working on expanding your skills and you wanted to create some sort of research to keep up with the current material, then you may want to use a deep research model. So AI can augment, but it will not replace SLPs. And that is the key takeaway here, is that an SLP using these tools can be more effective and do a lot of tasks. But in the end, you still are needed to do these tasks. These models will not replace, but they can augment. That is it for this brief overview of large language models, reasoning models, and deep research, some of the tasks they can do, specifically focused on SLPs. But I do actually eventually want to jump more into these different models. Specifically, I want to talk about the RAG modeling I talked about. I want to focus on the paper Attention is All You Need and dive a little bit more, because while I kind of am a little bit associated with this field, specifically, I'm actually focused on statistical and machine learning, which means that I'm more on the technical side of these large language models, and I actually work with others in the field who specifically are practitioners, which means that a lot of times my focus will be on the underlying models themselves, working with those with that domain expertise we talked about, allowing us to then create systems that are useful for both the technical and also the applied side of things. This presentation was adapted from a talk that I gave at SLP Tech Talk. If you're interested in knowing more about this, I'm going to put information in the description below with any links or anything like that, or contact if you're interested in joining. They do all sorts of topics every week. They meet up, they talk about different tech and how it affects SLPs, how SLPs can use it, things like that. And I think it actually could be a really good resource, and they're continuing to grow, and they have a lot of really interesting topics. So I'll put the information down below, and if you're interested, just follow that. And if you want to know more, you can always message me, and I can get you in contact with Leela, who's in charge of it. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.